Hello everyone and welcome to this part of Shaheen 101 training dealing with the running environment and job scheduling on our Cray XC40 supercomputer named Shaheen. My name is Sam Quarters. My colleague Mohsin Sheikh and I are delighted to be your hosts during this part of the session. We are both computational scientists in the team of Sabre. This talk has been pre-recorded but we are there for you, available to answer any questions you may write in the chat box during or right after the talk, and at the end of the whole training session. Anytime, feel also free to contact us via mail at our personal address or using the common address for support. For both of us, our goal is to give you everything you need to run your job on Shaheen. At the end of this talk of 25 minutes, you will know how to access Shaheen, how to manage your files and understand the role of the file systems involved, how to submit and monitor your computations, how to use software that are pre-installed on Shaheen. For Windows users, we will also present some nice tools to install that ease your interaction with our systems. I will talk first to present the runtime environment and Mohsin will show in 10 minutes everything about job scheduling. Then, coming next, just after the present talk, you will see two practical cases. How it happens in real life. Ru and Jiong will demonstrate two complete examples with a chemistry and a CFD applications. Finally, Bilal will show how you compile and debug your code efficiently on Shaheen. He will share priceless performance tips. So be sure to stay tuned. Before we start, let me just say a few words about my current occupations. I have been a computational scientist at KAUST Supercomputing Laboratory since September 2013. I am providing advanced support to our user. It can consist in tuning their codes or their workflow or providing them new tools. I am interested in putting everything possible to ease the access to our resources. Let's start. First things first, how to log in to Shaheen. As Sabre and Bilal mentioned, Shaheen is a big beast with more than 6,000 nodes available, almost 200,000 cores. To access these resources, you need to log in first to very special nodes, called the login nodes. You must be aware that these nodes are only used either to compile and prepare your code to be run on Shaheen or to submit your job and monitor it. Mohsin will tell you more on this in a few moments. To log to these nodes, we called CDL, you will use SSH. As Jiong will show you in a video soon after this talk, it is very simple. Just open a terminal window and type SSH your username at shaheen.hpc.kaust.edu.sa. You will be asked for two passwords. The first password are the same you use to log to your workstation at KAUST, to connect to the portal, to KAUST Wi-Fi access point or to read your mail. The second one is what is called a one-time password or OTP. It is composed of 6 digits and changes every 30 seconds. To have it, you will need to install a little application on your smartphone. When you open your Shaheen account for the first time, we will help you to set it up. Basically, it simply consists in downloading the app, and scan a QR code we give you to initialize it. The QR code is a seed unique to you that is used in the algorithm changing the password 2 times per minute. Your regular password must not be shared with anyone. We will never ask for it. The same with your OTP. If you are a Windows user, here is a solution to install a complete working and easy-to-use environment on your laptop or workstation. It allows you to log to Shaheen from Windows, have a bash terminal window, have access to Shaheen via SSH, move files back and forth between Shaheen and your Windows machine thanks to SCP, and forward a graphical output from Shaheen login node to your Windows machine. To install this environment on your Windows laptop or desktop computer, you can follow the instructions given in this very well-designed video on YouTube. It is from Software Carpentry. It has been already showcased by David Pugh when he gave the training Introduction to Shell for Data Scientists. It explains how to install Git, which is a versioning tool. What is really interesting is that it comes with a very neat installation of Bash and SSH included. Be sure to follow carefully every step. At the end of the installation, you should be able to open a terminal by starting the Git Bash application as shown in the YouTube video. From this window, you can then SSH to Shaheen, just as Xiong will show you, just as you would do from a laptop under macOS or a workstation under Linux. On our website, I put up a special page detailing the full installation of this environment. It's https://www.hpc.kaust.edu.sa/windows. It also describes how to install Xming on your Windows computer. Xming is an X11 server like Xquartz on macOS. It allows a graphical window from the CDL of Shaheen to pop up on your Windows screen. 2 conditions to achieve this. Start the Xming server. Add -Y when connected to Shaheen via SSH as Xiong shows it in its chemistry example. Let's also mention an alternative solution to Git Bash, which is PuTTY. Here is a link describing its installation. You will not get a full Bash environment installed, but it will also do the job. If you encounter any problem, feel also free to contact us. SPIAC. Alright. Now let's learn more about file systems and see how to transfer files back and forth. The first thing you need to be aware of is the structure of the file systems on Shaheen. We have 5 zones available to you: /home, /project, /scratch, the burst buffer and /tmp. Each of them has its own rules of usage and deletion policy. /home is a shared file system with our cluster Ibex. It's never deleted and its space is 200 GB allocated per user. Regular snapshots of your home are also in place and you have access to it in /.snapshot. You can retrieve previous version of files saved several hours or several days ago. An important thing to realize is that /home can only be accessed from the login nodes and not from the compute nodes. That's why you have to launch your job either from /project or /scratch. It is the only way for your job to start properly and have access to your data or the code you want to run. Classically, /home is used to store either things that are common with Ibex, or things you would like to store independently of project. /project and /scratch are 2 different zones of our Lustre file system. This file system is a parallel file system of 17 petabytes built on the top of traditional spinning hard drives interconnected with a high-speed network. Lustre is designed to deliver high bandwidth up to 500 gigabytes per second. Its features are the same whereas you use /project or /scratch. But the deletion and storage policies of these 2 zones differ. /project is used to store the essential data of a project, input files, codes, results that you desire to keep. The storage space on /project is allocated at the beginning of the project. All the files are only deleted at the end of the project. For /scratch, there are no limits in storage space, but any file older than 60 days is deleted forever. This process is fully automated and we cannot do anything to retrieve data deleted from /scratch. Therefore, classically, people are computing in Scratch and save their valuable data in /project. Be also aware of 2 important things. First, the Lustre file system is shared by all users. It is based on a set of servers, network cables and switch and physical hard drive, a set of finite resources. Sometimes, if too much users are conducting very intense input-output operations at the same period, it can then lag for a few moments. Hopefully, it only occurs a few times during the year for a few minutes. Second, the total number of files stored in Lustre is also limited. Therefore a quota on with the number of files per users is in place. This way, we prevent the filling of this shared and precious resource to be filled with non-vital files and invite users to clean their space on a regular basis. The limit is quite high though, up to 1 million files per user is allowed. The fourth file system is what we call a burst buffer. As it is based on SSD drives, it is significantly faster than Lustre with up to 1.5 terabytes per second. Its size is 1.5 petabytes. Its usage is slightly different than /Lustre or /Home. It has to be built at the beginning of a job and is destroyed at its end. Once it is allocated, it is all yours. It is accessible by all nodes in the job and only them. If you wish to access the burst buffer, please mention it in your project proposal. We will show you how to use it and we will put a training in place if people are interested. The fifth and last file system is a temporary space attached to each compute node and not shared among nodes. This space is /TMP. It is very fast, the fastest of all. Known as a RAM disk, it is in reality a part of the RAM used as a disk space. When using it you must be aware that the more you put files in /TMP, and the less memory you have available for your code and its data. Obviously /TMP is available to your job immediately when running on nodes. If you need any advice to optimize the usage of RAM disk, burst buffer or Lustre, feel free to contact us. In some cases, by tuning some parameters or using some tools we were able to make a code run several times faster. Okay, now let's see how to move files around. The only thing to bear in mind is that only the login nodes are reachable from the outside. But remember your code runs on the compute node and can only access to /project and /scratch. The strategy here is to transfer your files to the login node and be sure to save them either in /project or /scratch if you want to use them in your computation. From your workstation this can be done using the command scp accordingly to the syntax shown here. And here is the command to retrieve files from Shaheen to your workstation. I guess that's it from me for now. Feel free to ask questions in the chat box and by mail anytime. I will leave you now with Mohsin, who will address how to schedule, run and monitor a job. Mohsin, the floor is yours.
Hi, my name is Mohsin Ahmed Sheikh and I am one of the computational scientists at KAUST Supercomputing Lab. I'm going to talk about job scheduling on Shaheen. HPC resources must be kept busy at all times to maximize the scientific impact of such an expensive resource as Shaheen. Fairness of distribution of computational resources in such circumstance is also paramount. To achieve these objectives, job schedulers are used. In general, job schedulers allocate resources to jobs for a certain amount of time from a pool of resources. This allocation and its use is maintained and accounted by the job scheduler. This helps the scheduler to maintain priorities of jobs. Using job scheduler on Shaheen may need some changes to your workflow. Job schedulers run work on your behalf. This means you may need to script and automate your workflow. A benefit of doing so is that you can submit multiple experiments or simulations all at once and maximize throughput of your scientific investigation. On Shaheen, we use Slum for job scheduling. Slum primarily allows more work than available allocatable resources by managing the submitted jobs in queues, in running or pending states. It is also providing mechanism to manifest complex workflows, for example, dependent jobs or array of parameterized jobs. Slum provides a means of describing and submitting a resource request, configuring the use of allocatable resources to match the capability of the user's application, a means of monitoring the job status, and accounting the use of allocated resources. Let's jump into how users can interact with Slum. First, let's see how to query the status of system resources. sinfo is a useful Slum command which shows a concise report of the resources and their states. Available partitions or queues are listed in the first column. We'll be using the term partition and queue interchangeably. The second column shows the status of this partition or queue. The third column lists the allowed size in terms of number of nodes for each partition. For example, work queue allows jobs of size ranging from 1 to 6,158 nodes in this case. The fourth column lists the maximum allowed hold time for a job submitted to the respective queue. For example, work queue allows a maximum of 24-hour job, whereas 72-hour queue, as the name suggests, allows hold time for up to 72 hours maximum. Fifth and sixth column describes the maximum number of CPUs and the physical topology on the node. On Shaheen, hyperthreading is enabled, so each of the 32 physical cores support 2 logical CPUs, meaning 64 CPUs in total. Each node has 2 sockets. Each socket houses an Intel Haswell processor chip and has 16 physical cores. Each core can run 2 hyperthreads. Columns 7 and 8 together show the number of nodes and their states in each partition. For example, in the report we are seeing 6,016 nodes on work queue are allocated at the moment, whereas 142 are in idle state. Another useful Slum command to query the status of jobs is sq. sq lists every job by its job ID and tabulates the status, start and end times of the job amongst other things. It is usually a good idea to filter the output of sq by username, partition, or specific job ID for concise view. Slum provides a means of describing an allocation request as a collection of directives parameterizing the resources, including accounting and time requisites for the submitted jobs. Partitions, or queues, are pools of allocatable resources, pooled under global constraints such as maximum time or minimum or maximum job size, etc. Status of all the queues can be queried with sinfo to see what or how much is available to be allocated or is in use. Allocation requests can constitute of 3 computational resources and the duration for which they are needed by your job. CPUs, memory, and burst buffer storage are the 3 allocatable resources. And hold time is the expected time your application would require for these computational resources to be available. Users can submit their work as batch jobs to Slum or request the computational resource to run their work interactively. Batch jobs are composed of the resource request and the workflow steps to run when the requested resource is available, all in a shell script. Once submitted to Slum, it will execute the job script on user's behalf when the requested allocation is granted. For batch jobs, the hold time can be set for long durations and multiple jobs can be submitted if needed. In case the user wishes to prototype or debug a workflow interactive jobs or sessions can also be submitted. In this case, a resource request is submitted and control of the prompt is given back to the user to run the workflow steps interactively. Since these sessions are generally used for prototyping and debugging workflows, they are small in scale, ranging from 1 to 6 nodes, and short in time, a maximum of 30 minutes. Shaheen has a separate queue called debug to submit such interactive jobs. Let us now examine an example job script, which when submitted to Slum as batch job, will run on user's behalf. The first line starts a new shell, in this case, a bash shell. The next line, starting with #sbatch or #dw, are directives to Slum. The line starting with srun is launching a parallel application, WASP in this case, with 64 MPI processes. We ask Slum launcher to map each MPI process to a physical core by using the argument --hint equals no multithread. The job can be submitted to Slum by using the command sbatch. Sbatch is a command to submit batch jobs to Slum. Upon successful submission, it returns a job ID assigned to the job submitted. Upon being queued to a specified partition of Slum, the job gets scheduled and a priority value is assigned to it. The priority increases with the age of the job in the queue. In general, jobs requiring small number of nodes and short hold time are easier to schedule for the scheduler and run before others. Users can cancel a submitted job in any state using the Slum command scancel. Scancel requires a job ID as its argument. For submitting resource requests to start interactive session, the Slum command salloc or salloc is used. For example, if I need 2 Shaheen nodes from debug partition, I pass this resource request to salloc as its arguments. Once the resource is allocated, Slum notifies by a message granted job allocation and a job ID. Notice that the command prompt has changed a bit, and we are no longer on login node, but on a gateway node. From gateway node, I can launch my application on the compute nodes allocated to my job ID using the Slum command srun. The allocation persists even after the first srun command finishes. I can issue subsequent srun commands to run next steps of my workflow. Once prototyping is finished, I type exit, which terminates the interactive session allocated to me and the associated job, and takes me back to the login node. Slum allocates the requested resources to a job. The use of these resources are upon user's disposal, and the user can configure their use that best suits the multiple steps of their workflow. Here is an example of an interactive job asking for 2 Shaheen nodes from debug partition. Once allocated, the srun command can be used to configure the available resources to launch the job that suits the application requirement. In this example, the application Hello World is a hybrid OpenMP and MPI application. Srun command launches Hello World with 16 MPI processes each capable of spawning 4 OpenMP threads. --hint equals no multithread ensures that each MPI process and OpenMP thread runs on a physical core and not as a hyperthread. This is an example of a job script destined to be submitted as batch job. It demonstrates that the workflow has a pre-processing step which needs to run serially, followed by a parallel step in the workflow. The same allocated compute node will be used for both srun commands in the workflow. Jobs, once submitted to Slum queue, can be monitored and their accounting can be queried as well. sq is a Slum command to query the status of the job submitted. By default, sq shows all jobs in Slum queues. It can be filtered by username or by job ID for concise view of output. scontrol is another useful Slum utility to query the details of a job during its lifetime. When the job finishes, normally or otherwise, scontrol will not be able to retrieve these details. Among other things, it lists parameters such as node list, allocated to the job, and details of resource allocated. It is good practice to call scontrol command inside the job script so that it can snapshot the resources allocated to that job during runtime. sact is another powerful utility to query the accounting associated to the usage of a job or jobs by a user. By default, sact shows all your jobs that you have run in recent days. You can filter the output by job ID or username, account, or partition. sact shows a job and all the job steps associated with it. The fourth column has the account name to which the core hours of the job have been charged. Let us now see some example job scripts, which are commonplace on Shaheen. This is an example of submitting a batch job to run an OpenMP application on a single compute node of Shaheen. The application requires 4 physical cores to spawn OpenMP threads. This is requested through the parameter CPUs per task in the Slum directives section, and is also passed to srun command line as -c argument. Before launching srun, we set the environment variable omp num threads. srun command on Shaheen exports the environment set in the current shell by default. Next, we see the example where we submit a job script to launch an MPI application requiring 32 MPI processes. Again, notice that we use --hint equals no multithread to ensure each MPI process runs on a physical core. In this example job script, we try to run a hybrid code capable of using both MPI and OpenMP. The application requires 32 MPI processes and 4 OpenMP threads spawned by each MPI process. That is, in total, 128 physical cores will be needed for this job. The job therefore requests 32 N tasks and 4 CPUs per task. By default on Shaheen, the file I/O of an application uses Lustre file system. In some extreme use cases, where applications are I/O bound and require very high IOPS, the use of burst buffers is helpful. Burst buffer allocation can be requested in a job script by adding #dw directive. In this example, the keyword job_dw requests approximately 2 terabytes of scratch space with the striping feature. This scratch space will exist for the lifetime of the job. The next line sets the staging directory where the data should be placed on burst buffer file system. The line after this sets the path to stage out directory. This is the location on Lustre file system where the user would like the results to go after completion of the job.
Thank you, Mohsin. Just before handing the mic to the next ones, let me just point you to our Shaheen Job Generator that could help you to build your very first job. To use it, in a browser, just open the link shown here, then choose the desired resources based on what Mohsin has just shown you. Finally, click on Generate Job. You have a job example ready to be cut and pasted in a text file to be submitted on Shaheen. That's it for us, folks. Now I will leave you with Jiong and Ru, who will put in practice all that we have just introduced for real applicative examples. Jiong, the floor is yours.